In this recording, we discuss what we refer to as free body diagram. Okay, now I'm going back. I'm not going to run the simulation here right now, but these are snapshots from what I did before. You notice here we have the cabinet and we are pushing on it. The applied force is represented by this blue arrow, and the friction force is represented by the red arrow, and then it is shown as here what it's calling the total force, and it is pointing towards the right. And actually, if we were running the simulation right now, we'll see that the cabinet would be accelerating in the same direction as that force. And the idea behind this, that's my unbalanced force. Now, if we were going to apply Newton's second law of motion, we have to investigate all the forces acting on our cabinet. What are all the forces acting on it? In addition to this applied force and the friction force, there will be the gravitational force due to the earth pulling down on it along the vertical, and there will be a normal force due to the floor pushing up on it from the bottom. So these are the two other forces acting on it. They are both along the vertical, along with these two forces along the horizontal. If we were to write Newton's second law that says the sum of all forces, remember the sigma here says sum of all external forces acting on the cabinet, in this case, is going to be equal to m times a. And it is going to be also called the total force, or the unbalanced force, or the net force, whatever you want to call it. Now, in this case, these forces are going to be Fg, the gravitational force, the normal force, Fn, plus the applied force, I'm going to just label it F sub A, plus the friction force, F sub F. The sum of all of these is equal to Ma. And remember that these, if you notice here, these vectors are not along the same direction, so we cannot simply add them up. What we have to do is consider the vectors that are along the horizontal by themselves, and consider the vectors that are along the vertical by themselves. One thing to help us figure that out is what we call the free body diagram. That's the term, what we call the free body diagram. The way we do that, to simplify things, whatever we think of as forces acting on our object, we draw them by themselves in symbolic format using arrows without having to worry about drawing the object. Now, when we draw them somewhat like this, we can see distinctly what the forces are, and which forces are along the same direction, and which forces are perpendicular to that. For example, here we see that F sub n and F sub g, both of them are along the vertical, and both of these are along the horizontal. Now, F sub n and F sub g, we don't see any acceleration upwards or downwards, so that tells us that these two must be balanced. F sub n and F sub g, in this case, are balanced. And in this graph, in this diagram, we see them equal to each other. However, if we are noticing an acceleration along the horizontal, that would tell us that Fa and Ff are not balanced. And that's what we see here. Notice in the free body diagram, we don't have the net force or the total force drawn. Personally, I prefer it like that. We'll see in another simulation by the same group, they end up adding it. I don't like that. Why don't I like it? Because it might help the students think that what we call as the total force is an additional force acting on the object, which is not the case. What we call the total force is just the sum of what's in here already. So now here, Ff and Fa are in the same direction, but they are unbalanced. So Fa minus Ff is going to be my unbalanced force. It's FA minus FF because FBA is larger than FF. Okay, let's look at another case. In this case here, the cabinet is moving, but I'm not pushing anymore. So what is it doing? What's going to happen to it? Since I'm not pushing anymore, it was moving, there is a friction force acting on it. So if we look at it in terms of a free body diagram, FG and Fn are still along the vertical. They are not affected by the fact that I'm applying a force or not, since the force I'm applying is along the horizontal. So these two are still balanced. However, along the horizontal, we don't have any applied force anymore. We have only the friction force. And there is nothing to balance it. So my unbalanced force in this case, or my total force, is the same as the friction force. Now, since my motion is in this direction, and my unbalanced force is in the opposite direction, my cabinet is going to slow down and eventually come to a stop.